In this and the next video, I'd like to tell you about one possible extension to the anomaly detection algorithm that we've developed so far. This extension uses something called the multivariate Gaussian distribution. It has some advantages and some disadvantages, and it can sometimes catch some anomalies that the earlier algorithm didn't. To motivate this, let's start with an example. Let's say that our unlabeled data looks like what I've plotted here, and I'm going to use the example of monitoring machines in the data center, monitoring computers in the data center. So my two features are x1, which is the CPU load, and x2, which is maybe the memory use. So if I take my two features, x1 and x2, and if I model them as Gaussians, then here's a plot of my x1 features, here's a plot of my x2 features, and so if I fit a Gaussian to that, maybe I'll get a Gaussian like this. So here's p of x1, which depends on my parameters mu1 and sigma squared is 1. And here's my memory use. Maybe I get a Gaussian that looks like this. And this is my p of x2, which depends on mu2 and sigma squared 2. And so this is how the anomaly detection algorithm models x1 and x2. Now let's say that in the test sets I have an example that looks like this. Right, the location of that green cross. So the value of x1 is about 0.4 and the value of x2 is about 1.5. Now if you look at the data, it looks like most of the data lies in this region, and so that green cross is pretty far away from any of the data I've seen. It looks like that should be raised as an anomaly, right? So in my data, in the data of my good examples, it looks like the CPU load and the memory use, they sort of grow linearly with each other. So if I have a machine using lots of CPU, memory use will also be very high. Whereas this example, this green example, it looks like here the CPU load is very low, but the memory use is very high, and I just have not seen that before in my training set. It looks like that should be an anomaly. But let's see what the anomaly detection algorithm will do. Well, for the CPU load, it puts it at around there, 0.5. And this reasonably high probability is not that far from other examples we've seen maybe. Whereas for the memory use, I guess it's pointed at 0.5. Whereas for the memory use, it's about 1.5, which is there. Again, is out towards the tail of the Gaussian, but the value here is not that different from many other examples we've seen. And so p of x1 will be pretty high, reasonably high. P of x2 will be reasonably high. I mean, if you look at this plot, right, this point here, it doesn't look that bad. And if you look at this plot, across here, it doesn't look that bad. I mean, I have had examples with even greater memory use or with even less CPU use, and so this example doesn't look that anomalous. And so anomaly detection algorithm will fail to flag this point as an anomaly. And it turns out that what our anomaly detection algorithm is doing is just not realizing that this blue ellipse shows the high probability region. Instead, what it thinks is that examples here are high probability, and examples the next circle out are somewhat lower probability, and examples here are even lower probability. And somehow, things that are green cross there is pretty high probability. And in particular, it tends to think that everything in this region, everything on the line that I'm circling over has about equal probability, and it doesn't realize that something out here actually has much lower probability than something over there. So in order to fix this, we're going to develop a modified version of the anomaly detection algorithm using something called the multivariate Gaussian distribution, also called the multivariate normal distribution. So here's what we're going to do. We have features x which are in Rn, and instead of modeling p of x1, p of x2 separately, we're going to model p of x all in one go, so model p of x all at the same time. So the parameters of the multivariate Gaussian distribution are mu, which is a vector, and sigma, which is an n by n matrix called a covariance matrix. And this is similar to the covariance matrix that we saw when we were working with the PCA, with the principal components analysis algorithm. For the sake of completeness, let me just write out the formula for the multivariate Gaussian distribution. So we say that probability of x, and this is parameterized by my parameters mu and sigma, but the probability of x is equal to, once again, there's absolutely no need to memorize this formula. You can look it up whenever you need to use it, but this is what the probability of x looks like. Transpose sigma inverse x minus mu. And this thing here, the absolute value of sigma, this thing here, when I write this symbol, this is called the determinant of sigma. And this is a mathematical function of a matrix, and you really don't need to know what the determinant of a matrix is, but really all you need to know is that you can compute it in octave by using the octave command det of sigma. Okay, and again, just be clear, right? In this expression, these sigmas here, these are this n by n matrix. This is not a summation. The sigma there is an n by n matrix. So that's the formula for p of x. But more interestingly, or more importantly, is what does p of x actually look like? Let's look at some examples of multivariate or Gaussian distributions. So let's take a two-dimensional example. So if I have n equals 2, I have two features, x1 and x2. Let's say I set mu to be equal to 0 and sigma to be equal to this matrix here, with 1s on the diagonals and 0s on the off diagonals. This matrix is sometimes also called the identity matrix. In that case, p of x will look like this. And what I'm showing in this figure is, for a specific value of x1 and for a specific value of x2, the height of this surface gives the value of p of x. And so with this setting of the parameters, p of x is highest when x1 and x2 equals 0. So that's the peak of this Gaussian distribution. And the probability falls off with this sort of two-dimensional Gaussian, or this bell-shaped, two-dimensional bell-shaped surface. Down below is the same thing but plotted using a contour plot instead, or plotted using the different colors. And so this heavy intense red in the middle corresponds to the highest values, and then the values decrease, with the yellow being slightly lower values, the cyan being lower values, and this deep blue being the lowest value. So this is really the same figure but plotted viewed from the top instead, using colors instead. And so with this distribution, you see that it places most of the probability near 0, 0, and then as you go away from 0, 0, the probability of x1 and x2 goes down. Now let's try varying some of the parameters and see what happens. So let's take sigma and change it. So let's say sigma shrinks a little bit. Sigma is the covariance matrix, and so it measures the variance of the variability of the features x1 and x2. So if you shrink sigma, then what you get is that the width of this bump diminishes, and the height also increases a bit, because the area under the surface is equal to 1. So the integral of the volume under the surface is equal to 1, because probability distribution must integrate to 1. But so if you shrink the variance, it's kind of like shrinking sigma squared, you end up with a narrower distribution and one that's a little bit taller. And so you see here also the concentric ellipses has shrunk a little bit. Whereas in contrast, if you were to increase sigma to 2 on the diagonal, so this is now 2 times the identity, then you end up with a much wider, a much flatter Gaussian, and so the width of this is much wider. This is hard to see, but this is still a bell-shaped bump that's just flattened out a lot, and it's become much wider. And so the variance here, or the variability of x1 and x2, just becomes wider. Here are a few more examples. Now let's try varying one of the elements of sigma at a time. Let's say I set sigma to 0.6 there and 1 over there. What this does is this reduces the variance of the first feature x1 while keeping the variance of the second feature x2 the same. And so with this setting of parameters, you can model things like that. x1 has smaller variance and x2 has larger variance. Whereas if I do this, if I set this matrix to 2, 1, then you can also model examples where, here looks like x1 can take on a large range of values, whereas x2 takes on a relatively narrow range of values, and that's reflected in this figure as well, where the distribution falls off more slowly as x1 moves away from 0, but it falls off very rapidly as x2 moves away from 0. And similarly, if we were to modify this element of the matrix instead, then similar to the previous slide, except that here we're playing around. Here we're saying that x2 can take on a very small range of values, and so here if this is 0.6, right? Notice now x2 tends to take on a much smaller range of values than the original example. Whereas if we were to set sigma to equal to 2, then that's like saying that x2 has a much larger range of values. Now, one of the cool things about the multivariate Gaussian distribution is that you can also use it to model correlations between the data. That is, you can use it to model the fact that x1 and x2 tend to be highly correlated with each other, for example. So specifically, if you start to change the off-diagonal entries of this covariance matrix, then you can get a different type of Gaussian distribution. And so as I increase the off-diagonal entries from 0.5 to 0.8, what I get is a distribution that's more and more thinly peaked along this sort of x equals y line. Right? And so here are the contours. It says that x and y tend to grow together, and the things with large probability are if either x1 is large and y2 is large, or x1 is small and y2 is small, or somewhere in between. And as this entry 0.8 gets large, you get a Gaussian distribution that's sort of where all the probability lies on this sort of narrow region where x is approximately equal to y. Kind of there's a very tall, thin distribution, lying mostly along this central region where x is close to y. So this is if we set these entries to be positive entries. In contrast, if we set these to negative values, as I decrease this to -0.5 down to -0.8, then what we get is a model where we put most of the probability in this sort of negative x1 and x2 correlation region. And so most of the probability now lies in this region where x1 is about equal to -x2 rather than x1 equals x2. And so this captures a sort of negative correlation between x1 and x2. And so this is hopefully this gives you a sense of the different distributions that a multivariate Gaussian distribution can capture. So far we've been varying the covariance matrix sigma. The other thing you can do is also vary the mean parameter mu, and so originally we had mu equals 0, 0, and so the distribution was centered around x1 equals 0, x2 equals 0, so the peak of the distribution is here. Right? Whereas if we vary the values of mu, then that varies the peak of the distribution. So if mu equals 0, 0.5, the peak is at x1 equals 0 and x2 equals 0.5, and so the peak or the center of this distribution has shifted. And if mu was 1.5 minus 0.5, then again similarly the peak of the distribution has now shifted to a different location corresponding to where x1 is 1.5 and x2 is minus 0.5, and so varying the mu parameter just shifts around the center of this whole distribution. So hopefully looking at all these different pictures gives you a sense of the sort of probability distributions that the multivariate Gaussian distribution allows you to capture. And the key advantage of it is it allows you to capture when you'd expect two different features to be positively correlated or maybe negatively correlated. In the next video, we'll take this multivariate Gaussian distribution and apply it to anomaly detection.